Good morning and welcome to the third and last day of the second TwinBrain workshop. I hope the contents of the previous days were thought-provoking and you found them interesting. My name is Manca Peskar, I work at the Science and Research Center Koper and I'm going to be moderating today's session. So today we are moving away from the peripheral nervous system, away from the muscles and kinematics, and we're kind of traveling upward the signal propagation hierarchy to the brain, if I may say so. However, we will not be neglecting movement. We will also approach the exploration of brain dynamics using the preferred method for tracking brain dynamics in time and in mobile settings, using electroencephalography, or EEG in short. So today's agenda will walk us through the basics of neurophysiology, designing of ERP experiments, and investigating measures such as signal-to-noise ratio for keeping the quality of the signal high. After the break, Valentina Bianco will be joining us online, so I encourage you all to post any questions you might have in the discussion on YouTube. Taking it from there, our next speaker, Klaus Gramann, will dive into independent component analysis, explain us why is it used, and how rejecting independent components might be a useful approach to data cleaning, and from which point on it starts interfering with the results in an undesired way. So as a continuation of his talk, we will then listen to Noelle Jacobsen, who will show how independent component analysis algorithm could be improved by training it on mobile EEG data. After the lunch break, we will dive more into the analysis approaches to EEG data, and first, Fiorenzo Artoni will present us with some connectivity measures, specifically cortico-cortical and cortico-muscular coherence, and finally, Aleksandar Miladinović will take us on a journey to time-frequency analysis and gate-related spectral perturbation. All the materials of today's sessions you can find on the Dropbox link that our team will post in the chat. So enjoy Valentina's talk, and we come back live for this.
During my talk today, I'm going to provide first a short overview of the EEG technique in general. Then we will focus more on event-related potentials technique. And then we are going through the design of the ERP experiments. And after that, we are going to provide, let's say, a pipeline of the more typical ERP analysis. And finally, we are going to provide an example of ERP analysis on a data set. And last, I'm going to provide an example of ERP studies, so of the application of the ERP technique. So what is electroencephalography? We can say that the raw EEG can indicate general state, but it can't tell us much about specific neurocognitive processes. But basically, what we are recording are similarly oriented groups of cerebral cortical neurons near the scalp, where the recording electrodes are usually placed. And these are usually reflecting the activity of pyramidal neurons, more specifically in layers 3 and 5 of the cerebral cortex. And this is going to be reflected on postsynaptic potentials. So let's say that what we see on the scalp, what we register during the EEG reading is not action potentials, but is the activity of postsynaptic potentials. What happens at, let's say, cellular level? So for each neuron, we're going to have a neurotransmitter who is going to arrive to the dendrites, the apical dendrites, and this is going to be reflected in an excitatory or in an inhibitory neurotransmission. And what happens is that basically most of the pyramid cells were directed toward the same direction are going to be excited or inhibited at the same time. And so what is going on at each single neuron is going to be reflected on the scalp. And so the sum of these neurotransmissions are going to be reflected in a, let's say, in a dipole, okay? In a dipole with a negative and a positive pole. So how when we register the EEG activity, it's common use to have a system to which we can refer when we collect data, basically. Most of the time we have some reference points like the nasion, the inion, the left and right preauricular point. And then each electrode has a name, which indicates the brain region, basically. And also we have numbers, and all the numbers are reflecting the left hemisphere, while the even numbers are reflecting the right hemisphere. And the higher we are going far from the midline, the higher is the number of the electrode. And basically, all the electrodes are considered the active electrodes, so where the EEG recording is happening, and they are considered unipolar electrodes, in that we usually measure the difference between each active electrode and a reference, which is common for all channels. Indeed, we have this kind of terminology, active, reference, and ground electrodes. And what we are measuring on the scalp is always a difference between the active and the reference electrode. And it's very important where we place the reference electrode. This is usually a crucial information that we have to provide in papers, because the reference electrode should be placed at a neutral site. But it's very difficult, basically, to find a neutral site. So what are we doing here is just to show you how is different the recording, how is different the activity we are collecting, we are recording on the basis of the reference we are placing our electrode. So you can say that you can have literally huge difference in amplitude in this case of the event-related potentials if you're placing the reference on the nose, on the earlobes, on the mastoids. So what we do during EEG? During the EEG, we try to pull out specific segments, okay? We try to isolate specific moments of the recording in which we can extract crucial information on the basis of our research question. But most of the time, for sure, we have to have some reference, some markers, and the most common used are, of course, the stimulus and the response. So we have to know when is happening the stimulus appearance and when is happening the response of the subject. We have two ways to analyze the EEG once we collect the data. In this case, we're just having an example of a 64 EEG cups, and these are the 64 EEG channels. And so basically we can measure, we can analyze the ERP, the EEG on the frequency domain or on the time domain. And so we are focusing today on the time domain. And from that, we can focus on the event-related potentials, which are defined as deflections, which are time-locked and elicited by the repeated occurrence of sensory, motor, or higher order events. In the example below, we have that, for instance, 0 is the stimulus onset, and so we have some sort of components which reflect different sensory and motor functions or cognitive functions. These are depending on the sensory modality in which we are providing the stimulus and on the type of task, basically. One crucial distinction we can do is between the synchronizing, let's say, the signal to the stimulus onset, or synchronizing the stimulus, for instance, to the movement, okay? Because sometimes you are not interested in what happens after the presentation of a stimulus, but we are interested in what happens, for instance, before the beginning of a movement, okay? So in this case, on the right, we see that the 0 in this specific case is the beginning of the movement. And we can study the BP we will see later is the typical motor premotor component. Another information, basically, when we refer to the ERP, we call PON, referring to the positive going or negative going. And then we have to say that there is no universal convention for plotting the negativity up or down. In this case, the negativity is plotted down, but in some papers this cannot be plotted up. A crucial advance that we did basically in our lab, but not only in our lab in Rome when I was studying, when I was investigating anticipatory ERP components, is that we tried to study what happens not only before, for instance, the beginning of a movement, but what happens before the presentation of a stimulus. And this point of view, this new way to analyze the data allowed us to explore a large variety of functions that have been largely unexplored in the past. Because as I told you, basically, you usually record event-related potentials after the presentation of a stimulus or before the beginning of a movement. What is crucial when we analyze, when we reason about the ERP are their amplitude and their latency. So these are crucial because peak amplitudes and latencies reflect discrete sensory and cognitive processes, and they are largely depending, as I told you already, on the task we are using and on the sensory modality. In a typical experimental setting, we have a cup in which there are electrodes, and it's very important that in these electrodes we put some conductive gel, which allow us to provide a bridge between the electrode and the scalp. This is a typical setting, complete setting. The most important part of the settings, of course, are the stimulus presentation computer, the computer which allows the digitization, so to register the EEG, and most of the time you also have a third monitor to monitor the behavior on the stimulus presentation computer. And then the participant usually wear a head box connected to the cap, and of course the signal has to be transformed from analogic to digital, and this is usually done thanks first to the amplifier and then to the digitization computer. The most one crucial but is not usually done is that we should place the subject into a electrically shielded chamber, which protect, let's say, from the interference of, for instance, from current. Basically, when, as I told you already, when you register the EEG, you also want to have event codes, the stimulus for sure, and the response. And also you have to choose a sampling rate. And usually is a sampling rate between 250 and 1000 hertz is recommended, because the sampling rate must be more than twice as high as the highest frequency in the data to avoid the typical aliasing. Let's go through the typical ERP analysis pipeline. So when you record the EEG and then you want to arrive to get the ERP, you have to do some sort of pre-processing. The first thing you have to do, and also you have to take into consideration during the recording, is to record the ocular movements. Okay, and so this is going to allow the ocular correction. After that, sometimes it happens that some channels just don't work. Okay, we usually have 64, 120 channels. Sometimes some of them just don't work. And we can do a topographic interpolation. After that, a crucial, very crucial step is the filtering. And then we go deeply through this later. After that, we do the artifact rejections. The artifact rejection allows to remove selected time intervals after they are not, resolved from the previous steps. And then we going to segment the channel, the recording in epochs of interest, actually. And then we are going to do the typical average. So from, for instance, 300 segments, we're going to have one. The average or the individual average of a specific event of interest. Then we will perform the baseline correction, and then after we collect the data from multiple subjects, we are going to perform all the steps, and then we're going to have a grand average, so a group level. Ocular correction, first step, the most commonly used are the Gratton and the Young. So the Gratton is based basically on literally a difference. So you measure by means of bipolar recordings, usually, the movements done in the ocular from the movements done from the eyes, and then you literally do a sort of you subtract that from the activity that you think is contaminated from ocular corrections, from ocular movements, from the EEG recording. Of course, the more contaminated electrodes are those we are placed on frontopolar electrodes and frontal electrodes. And the Young correction is usually more precise in that it is going to actually doing independent component analysis. So here, let's say that it's more precise because it's gonna provide doing an analysis of the composition of all the signals and extracting what is thought to be connected to ocular movements from the EEG. The topographic interpolation is very easy. It just performs a reconstruction of omitted or missing channel signal based on a weighed sum of signals from the neighboring channels. Filtering is the most important step of the preprocessing. So we are going to have the low pass and the high pass. Low pass is also known as high cutoff, and the high pass is also known as low cutoff. So the low pass is going to remove the high frequencies and to pass low frequencies. So here you can see an example of the unfiltered ERP, and then here you can see an ERP low pass filtered at 30 Hz. Why it is important to choose an appropriate filter? Because here on the right you can see the effect of, for instance, of a 12 Hz low pass filter. So when it's not high enough, you literally have a distortion, okay, of the original ERP. And this is going to have going to generate problems, because this is going to generate shifts in the latency and the amplitude of the original ERP. So you are going basically to mess the results. So it's very important that you choose a high, filter. And you should never go below. Then we will see later the recommended filters. So the high pass is going to remove the low frequencies and to pass the high frequencies. Here you can see an example of the unfiltered EG and of a EG filtered at 0.1 Hertz. Again, on the right, you can see the distortion of using not too low filtering. You can see here, if you use 0.01 or 0.1 is good, but if you're going to increase the filter, so 0.3, 0.5, 0.7, then 1, again, you're going to have huge distortions. In this case, especially on the amplitude. So also in this case, you're going to mess the results. These are the usual recommendations. So don't worry if the high pass cutoff is less than 0.1 or higher than 20 Hertz, and worry a lot when the high pass cutoff is higher than 0.5 or lower than 10 Hertz. As I told you, after doing the filtering, the ocular correction, and the topographic interpolation, sometimes you still are not able to have clean data. You don't have clean data, so at this point, you have to remove specific segments, specific parts of the recording. And I usually use the brain vision analyzer to analyze data. And here I just can show you that I have some very, very huge artifacts, basically because this subject did the huge ocular movements that could not be corrected earlier. So in this case, I say, okay, we have to remove these pieces of EEG. And there are different ways you can do, there are different criteria you can choose to remove the artifact. I usually recommend to use the maximal difference, maximal allowed absolute difference. That should be 100 microvolt. If you have a very dirty data, you can also go to 150 and 180. But basically, if the subject has not very clean data, it's good to not to consider the subject in the analysis. This is my first recommendation. After that, you do the segmentation. So you extract the segments of EEG in relation to the event of interest. This depends on the task. Always you have to take in consideration that you also will need 120, 200 milliseconds extra for upcoming baseline correction. For instance, if we have a stim, and then we also have to consider if we have to perform analysis on what happens before stimulus presentation or after stimulus presentation. This is going to change a little bit. For instance, if I'm interested in EEG activity occurring after, so the typical event-led potential analysis, I can do as a segmentation windows minus 200 milliseconds before the stimulus and 900 milliseconds post. If I'm interested in activities occurring before and also after, but also before, I can leave the 900 milliseconds post-stimulus, but maybe I can go more on the left, for the segmentation window, and going to, for instance, minus 1,100 milliseconds. After segmenting, what do? You just average all the epochs. You're going to have hundreds of epochs of interest on the basis of the specific task you are doing. And from that, so you're going to average the ERP, and you are going to get the typical ERP waveforms that you usually see on the papers. Of course, the more you have epochs, the best is, because the average is going to be cleaner. After the average, you have to perform the baseline correction because basically you have to subtract the estimate of offset voltage from the waveform. And usually the mean pre-stimulus voltage is usually a reasonable estimate of this offset voltage. And what you just do is just to subtract this value from each point in the waveform. So if in the recording you have the red signal after the baseline, this is going to go down, let's say, no? And then you have a baseline correction for all the recording, because the offset is usually due, for instance, to the skin potentials. Be careful here to the baseline, because we don't want to have blips in the baseline, because if the baseline is dirty, okay, is contaminated, this is going to be reflected on what happens after. So on the amplitude, for instance, on the of the ERP. So be careful that if you see some blips in the baseline, you have to worry a lot, and maybe to consider to remove the subject from the analysis. After you have collected more and more subjects, finally you're going to get a grand average. So the group average is usually what you see in the papers. A crucial aspect that we have to take in consideration when doing EEG, especially with the event-related potentials, is the signal-to-noise ratio. What is this? It's a typical measure of the capacity to distinguish the disk signal from noise. Okay. It is simply calculated as the ratio of the signal amplitude to the noise amplitude. And it can be shown that in the computation of an ERP, the signal-to-noise ratio increases as a function of the square root of the number of trials, provided that the noise is Gaussian distributed. This means, for instance, that we need to increase the number of trials by a factor of 4 to double the signal-to-noise ratio. What is the point? Is that when we are thinking to ERP experiments, we have to be very, very careful. In that we have to plan. I know that it's not good for the subject to stay a long time not doing the experiments, but depending on the task we are doing, we have to consider to have a lot of trials of that, because only the increasing the number of trials is going to allow me to be sure that I'm getting true signal, and I'm going to cancel out the error, let's say, the noise, okay? How I can improve the signal-to-noise ratio is to try to focus on performing a clean, okay, recording. I have to be very careful during the recording, not later during the analysis. While I'm recording, I have to be very careful that I'm monitoring the eye movements, the subject, the muscular activity, the cardiac activity, the skin potentials, and I have to control for these biological artifacts. I can do that. I can just ask the person to try not to blink too much, for instance, and if you have a muscular artifacts, you just have to ask to be more relaxed. So take your time, okay, when you do the recording. And another crucial advance to try to lower the signal to noise ratio is to, I don't know, it's not very common, but using the Faraday cage, because electrical current in any room with electrical wiring and any other electrical equipment in close proximity to the G sensors can actually have an impact on the signal, okay, on the quality of the signal. And another crucial, very, very crucial, maybe the one of the most important aspect to take into consideration is to check that the person we are recording is not having too much alpha. Alpha activity are oscillations of 10 hundredths of 10 hertz, and they are very, very similar to what we are looking for during the ERP analysis. So this is not good. These are going to create problems for the analysis, because they're going to be overlapped with what I need, okay, with the signal. Another aspect of the ERP is that we are usually seeing when we are going through a ERP paper. What we see are, on one side, we see the epochs, okay, basically the epochs, so the ERP, but you also have usually the topographic maps. So why they are important? Because they allow us to see not only what happens at single electrode, because usually you report the ERP at single electrodes, but also what is happening on a scalp level, to have an overall picture of what is happening. Because, for instance, some activities can be focal, as in this case, but can also be, for instance, by unipolar or bipolar, so can stay on both the right and the left hemisphere. So the topographic maps allows me to have more information, not only on the positivity or the negativity and the location of the single ERP, but also on how, for instance, that ERP is spread over the near electrodes or is more focused. Now I want to provide an example of all the steps we have talked on a data set, okay? So let's say that this is these are raw data. I must say that I collected this data. We can say that they are very clean, okay? These are the 64 channels. On the top we have the ocular channels, so the vertical and horizontal movements, and also we have, for instance, all the prefrontal electrodes, the central electrodes, and the occipital electrodes. And then we have the markers of events. Here we can say that S1 and S2 are, this is a go-no-go task, so it's a task when you have to respond to some stimuli and not respond to other stimuli. And S6 is, so S1 is an example of go, and also S2. S1 and S2 are go stimuli. S3 that we don't see and S5 are no-go signals. S6 in this case is the response, okay, the response of the subject. As I told you, these are very clean data, so we are not going to see much of the filtering, but in this case, I just I performed the filtering, and we saw that we don't have huge transformations of the data set. But for instance, what we can see is that some channels are flat, like the F9 or the C4. So these channels must be interpolated. So we will perform the topographic interpolation, and we have this data set. And now we want, for instance, to remove the contaminated channel. We want to remove the signal, the ocular movements from the contaminated channels. As I told you, that are especially the prefrontal and the frontal ones. And then you can see the result of ocular corrected signal. In this case, I performed independent component analysis. Now it's time to remove pieces of signals containing artifacts, because after doing all these steps, as I told you, and you can see that this is only part of the entire registration. Here I got like 320 trials, go trials, and 320 no-go trials. Okay, we are talking about hundreds of trials, okay, for an event of interest. Here, so we are going to do the artifact rejection, and I used 100 microvolt peak-to-peak, as I already showed you. So now I have this data that are filtered, that are clean. I rejected the artifacts. So now it's time to perform the segmentation. So I want to isolate the Go trials that are the S1 and S2 markers. As I told you, the S6 is the response trigger. So I'm very interested, for instance, in the Go trials which were followed by a response, okay? And also isolate the no-go trials, so S3 and S5, which are that I established, that they were the no-go triggers, no-go markers. Now, what I show here is just the result of a segmented no-go signal. What changed here is just the montage, okay? So here is more similar to what is happening on the scalp. Here is the prefrontal, frontal, central, and occipital, as mimicking what is going on the scalp. And now, as you can see, what is the difference from here to that is just that this is one trial. This is the average of all no-go trials. As I told you, these are 320 trials. As you can see, the signal is very clean, no, compared to this other one, which is a single trial. Then, even if this is not very visible, I performed what I said, the baseline corrected trace. And the next step is to focus, for instance, on an electrode in particular. I went to the FZ, so just a frontal electrode. And here I am focusing on the typical N2. The N2 is a very common ERP component related most to conflict monitoring, to inhibition. There are a lot of interpretations, but you just want to show you that. So in this case, we have the electrode here, the trace, and on the right, I also get the topographic map. The topographic map allows me to say, okay, well, maybe if I want to perform analysis, instead of choosing only one electrode, I can choose a cluster of electrodes, because the activity is very spread, no, over the scalp. It's not very focused only on one electrode. And I also get information on the latency, so what is the peak latency of that component. Here, I want to show you a typical ERP study that I performed in my lab, my previous lab actually. And just give you a short introduction of the study, and then I show you how I used the ERP technique. So here I was interested to study the differences between two specific athletes, type of athletes, so fencers and boxers, and to confront them with controls. I was very interested in these two types of athletes because fencing and boxing are both combat sports, okay? So they are both sports in which it's very important to be to have prompt and responses, not to be ready to change also decisions. So decision making is crucial. It's crucial also to have anticipation. You have to anticipate the movement of the opponent, no? And there are some differences. For instance, the fencing is based on a scoring system that says that every time you touch the person with the sword, you get the point. This is not true for boxing because it's not true that for each single for each single hit you get points. Okay. So there are some, the main difference is also that the boxing requires more physical contact than fencing. Here, what I did, they were recruited and we did a go-no-go task. The go-no-go task I already told about this task. So you have to respond to specific stimuli and not to respond to other stimuli. Doing that, you are allowed to measure how fast you are, how good you are to respond fast to proper stimuli, to target stimuli, and not to respond to when you shouldn't respond, no? As in the case of no-go. And you can measure the commission errors and the omission errors. Commission errors are called also false alarms, so it's a no-go and then but you respond, and the omission is that when you have to respond but you don't do, okay? So we performed the go-no-go task, and what we saw is that both athletes were very fast, so they were both faster than controls. But we saw huge differences for what concerns the errors, especially the commission errors, so the false alarms, so the response to no-go. As you can see, the fencers were very accurate, so they were very fast and very accurate. But the boxers were very fast, but not so accurate. They did the double of errors compared to fencers, okay? So this is already a very good behavioral result, but we could add some information on what happened at the neurophysiological level thanks to the ERP. And I only show in this case today how we use ERP technique to explore anticipatory brain activity. So the question was, is there some markers, no? Some EEG markers, some ERP marker that can say to me that maybe the fencers are going to be more accurate and the boxers are going to be less accurate, okay? So what we did is that we recorded the EEG during the performance of the go-no-go task, and here I only show you the focus on the anticipatory EEG, anticipatory ERP, okay? So what we did here is that we focused on specific components that are the Bereshaft potential. The Bereshaft potential is considered a premotor component, an anticipatory component, motor index, considered a readiness index, and the prefrontal negativity, which is instead considered a cognitive component, okay? And it has been shown that can represent anticipatory cognitive control. So as you can see, the BP, which reflects motor readiness, was higher in both athletes compared to controls, and this correlated with the response time. So the higher the BP, the faster the response time. And this was true for both fencers and boxers. But when we move to prefrontal electrodes, where we could record prefrontal negativity components, we saw that the prefrontal negativity component was higher only in the fencing group. So just having a look to this scheme, okay, this overview of what happens at electrophysiological levels, we can predict what is going to happen at behavioral level. Then we can say that there were a lot of interpretations on why this happened. But what is the focus now for you, the take-home message is that the ERP, the anticipatory ERP, allowed us to predict the performance. So I really thank you for the attention. And I hope to see you in presence in the future. And I'm here to answer all your questions. Thank you.
Hi, Valentina, and thank you so much for the nice talk, for a lovely overview. Thank you so much for joining us live now. So we had a question about your pre-processing pipeline routine. So you mentioned the cleaning of continuous data based on the automated 100 microvolt threshold. However, we had a question, what about visual inspection and eliminating all the bad EEG signal at the very beginning? So how do you treat this, and can you please elaborate on it a little bit?
So first of all, good morning to everybody, and very glad to be here, and thank you for this question. So you have to know that when you record the EEG data, it's very difficult to have clean data. So as I already explained, honestly, what I didn't say in the seminar is that sometimes some subjects are just not good, because you realize that even if you are there, if you are doing if you are lowering the impedance due to the fact that you didn't put enough conductive gel and whatever, some subjects just are not good. And maybe in that case, it's a good idea just to not perform the registration. Anyway, it's a good idea also to, once you get data, it's a good idea to, and eventually to perform a visual inspection and try to eliminate the EEG that is not good. But I also have to tell you that even if you can do that, on the other hand, you risk to cancel too much of signal, because most of the time the noise is not spreading out around all the electrodes. Let's see, now we have 64, 128. Sometimes you just have very isolated, for instance, noise. And it's, as I told you, since we want always to save as much as of EEG as possible, because if you have a lot of number of trials, you are sure that the signal to noise ratio is high. It's better to try at least to perform all the pipeline. I mean, you can also do both. You can do the visual inspection at first, and then during visual inspection, you just try to eliminate. But I also recommend to also do the preprocessing, because sometimes you have to correct. You can correct the problem on one channel, and in this way you save all that segment that are related to that time interval. And but anyway, the preprocessing is you can also do a semi-automatic preprocessing. So on one side, you can still have a visual inspection and also try to remove trial to trial during the preprocessing.
Yeah, thanks a lot. Yeah, so inter-individual variability is indeed very high, and it's hard to tell which participants will have a good EEG recording in advance. Yeah. Okay. Well, so we touched also upon the signal-to-noise ratio. So you provided us with a nice formula to kind of get to an estimate of how many trials we would need to get a good signal quality. However, typically when we look at the papers, there's at least above 30. I think it's kind of like a golden standard. So averaging 30 trials should kind of be the minimum requirement fulfilled. So what do you think about that? Until how high do you think would be reasonable or useful to go, and until which point it might be, let's say, an overcompensation for the signal-to-noise ratio?
In my opinion, it really depends on the task, because depending on the task, in my case, now I perform a go-no-go task 50%. So in that case, I can go for as I told you, a 300 go and 300 no go, and for sure, I'm sure that although I have noise, although I have to remove, for sure, out of 300 trials, 150 survive, even if the subject is not so clean, for instance. But there are some tasks in which, for instance, you cannot get so many trials, as in the case of, first of all, for the go-no-go, just 75 go, 25% no-go, or in the example of the audible task. In the audible task, what you do, you perform a train of the same stimuli, and then you have to, from time to time, you have to add a dissonant stimulus. But of course, the trials you are getting for the dissonant is going to be 5 or 6 times less than the other ones. So in that case, when you are focusing on, for instance, on errors, there are some tasks in which you are you want to explore the error negativity, which is a very common ERP related to errors, of course, you have to lower your expectative. In that case, it's very important to have clean data and to be sure that you are not removing parts of segments connected to the error. But in that case, you can also have like 20. 20 is the minimum, though, that you should at least collect. Because if out of 20 you remove 5, it's already a lot. So at least 20 you should have, for instance.
Okay, perfect. Thank you. So if we stay on the signal-to-noise ratio, and we think about like moving from stationary to mobile EEG experiments, right? So I think that I was actually thinking about like whether could we come up with a new or an updated formula, the square root of the number of trials that should be proportional to the signal-to-noise ratio for the mobile EEG experiments. So what do you think of this, and do you think like it's something that could be kind of like uniformed across the MoBI experiments, or yeah, what do you think?
Well, I think that maybe I'm not an expert of MoBI, and I'm very happy that later I'm gonna have some talks about that. But for sure, I performed, for instance, EEG doing the steps, but they still were not MoBI equipment. In that case, for sure, you can also be, I guess, for MoBI, you are mostly recording what happens during steps, basically, I guess. That is the most important advantage now of MoBI, that you can monitor what is going on online during the movement, for instance. I'm not sure that we can apply the same rules of the ERP. And I'm also thinking that for MoBI, you should not, maybe not thinking to event-related potential technique, you should move to other types of analysis. In that case, I believe that it's the case that you are, of course, having at least also 10, 20 good trials, but for sure, I don't see very well the possibility to have ERP analysis applied to MoBI. But this is my only my opinion. I'm still not on the updated about the if there are any updatings on the mobile systems which are advanced.
Yeah, it would be nice to get to a simple formula that would always tell you this is the number of trials you have to achieve, yes, and then you would be satisfied and good to go. Okay, we have another question about the anticipatory activity and its similarity to the CNV.
Yes.
So how are they similar?
Yes, they are very similar for some reasons. The CNV is also known as contingent negative variation. The main difference between the Bereshaft potential and the contingent negative variation in general is that to get a contingent negative variation, you must have a task in which you have two stimuli which have a different meaning. You must have a first stimulus that is going to tell you, wait, be prepared because something is coming. And then you have a second stimulus, which can be a stimulus which is visual, auditory, and whatever, to which you have to do something. And the contingent negative variation is the slow wave emerging between the warning stimulus and then with the target stimulus, okay? So to have a contingent negative variation, you have to have an expectancy and to be prepared to respond to some sort of stimulus. Instead, the Bereshaft potential does not need to have a warning stimulus and then a target stimulus. You can get the Bereshaft potential also before the stimulus, before, for instance, the movement, but also before a no movement, because we also get, for instance, Bereshaft potential before a no-go signal, because BP represents general motor readiness in the case you are performing a task. some authors believe and agree that the final part of the contingent negative variation, so the part very close to the beginning of the movement, coincide, so is equivalent to the Bereshaft potential.
Okay, well, Valentina, thank you very much again for joining us, for the lovely talk. All the best to you, and we will come back to the program after a short coffee break.
Thank you.
Thank you.